Welcome back to the Item Software Risk Analysis training tutorial. This is part 4. In our previous section, we successfully transitioned from theoretical concepts to a practical case study by examining a pressurized reactor vessel. We established our system boundaries, defined our analysis resolution, and identified the critical defense in depth layers that protect the system, the automated electronic safeguards, the human protection layer, and finally, the passive mechanical relief valve. Now that our system scope is locked in and our event table is ready, we are prepared to move into the actual modeling phase. As we move into modeling, it is important to recall the two primary paths of analysis, the deductive and inductive methods. Deductive reasoning is a top-down approach. We start with a major system failure and work backward to identify the combinations of root causes that make it possible. In contrast, inductive reasoning is bottom-up, starting with a single component failure to see how it propagates through the rest of the system. For the first part of our modeling work, we will focus on the deductive method. We will begin by introducing the most widely used tool for this top-down approach, fault tree analysis. So what exactly is a fault tree? At its core, fault tree analysis is a graphical, deductive technique that focuses on a single, specific undesired event, which we call the top event. This might be a catastrophic failure, like the vessel explosion we discussed in our case study, or any critical system-level hazard. The analysis works backward from that top event to identify the various pathways of equipment failures, human errors, or environmental factors that could lead to it. By visually mapping these relationships, the fault tree helps us systematically break a high-level hazard down into its fundamental root causes. This structure allows us to see exactly how individual component failures can propagate upward through the system layers to create a major incident. To build a functional model, we use logic gates to define exactly how lower-level failures combine to cause a higher-level event. The three most common relationships you will use are the OR, AND, and VOTE gates. The OR gate represents a situation where the output event occurs if at least one of the input events happens. In this logic, the failure pathways are independent. If any single branch fails, the failure propagates upward. This is the standard way to model series systems where no redundancy exists. The AND gate represents a much more restrictive relationship. Here, the output event occurs only if all the input events occur simultaneously. If even one input remains functional, the output event is prevented. This logic is the primary tool used to model parallel systems and redundant safeguards. Finally, the VOTE gate, often referred to as M out of N logic, is used when a specific threshold of failures must be met. The output event occurs if a minimum number of inputs, M, fail out of the total number of available inputs, N. This is a versatile relationship used to model partial redundancy or systems that require a majority of components to be operational to succeed. Understanding these three basic building blocks is essential, as they dictate how probabilities will eventually flow through your model. The item toolkit supports a wide range of specialized gates to handle complex behaviors, including the inhibit, priority, and XOR and NOT gates. These allow for modeling specific conditions or sequence-dependent failures. Additionally, the toolkit includes the transfer gate, which is essential for organizing large projects by linking subtrees across different pages. While we will focus on the foundational and or gates for this tutorial, we will explain the practical use of the transfer gate when we move into the actual modeling phase. Just as we have a library of logic gates, the item toolkit provides several event types to represent the different ways components fail and how we interact with the model. The most fundamental is the basic event. This represents a primary failure at the component level that is not broken down any further. This is where we will eventually assign our specific failure rates and probabilities. Next, we have the house event. These act as logical switches that can be set to true or false. They are incredibly useful for modeling different system configurations or operational phases without needing to rebuild the entire tree. We also use undeveloped events as placeholders. These represent failures that we have chosen not to analyze in detail, perhaps because they fall outside our current scope or we lack the necessary data to break them down further. Finally, the toolkit supports dormant events. These are specifically used for latent failures, failures that aren't immediately obvious during normal operation and are only discovered during a test or when the component is called upon to work. For the practical models in this tutorial, we will focus primarily on the basic event to represent the failures of our valves and sensors. The actual steps for building a fault tree follow the same general procedure we established in Part 3. We begin by identifying our top event, defining the scope, and selecting the appropriate resolution for our analysis. However, it is important to remember that fault tree analysis is often a multi-iteration process. It is rarely a straight line from start to finish. Once you begin constructing the logic, or even after you reach the evaluation stage, you may find it necessary to go back and refine your work. You might discover that you need to adjust your resolution, either drilling down into more detail for a critical system or simplifying an area where the risk is lower than expected. This constant refinement ensures the final model is both accurate and efficient. To ensure our fault tree is logically sound and easy for others to follow, we must adhere to a set of fundamental construction rules. First, always maintain a consistent top-to-bottom flow. Each level should clearly state the immediate cause of the event above it. Avoid skipping steps or jumping directly to root causes. This ensures that no intermediate failure modes are missed. Second, focus on the immediate, necessary, and sufficient causes. When looking at a gate, ask yourself, are these inputs the immediate reason for the failure? Are they all necessary? And taken together, are they sufficient to cause the output? Finally, pay close attention to event naming and labeling. As we discussed in our ground rules, using a standardized naming convention makes the model much more readable. By following these structured construction rules, we create a logic model that is not only mathematically accurate, but also serves as a clear communication tool for the entire engineering team. That brings us to the end of Part 4. We have now covered the logical building blocks of fault tree analysis, from the various gates and event types supported in the item toolkit to the fundamental rules of construction. We've established how to translate a top-level hazard into a structured, deductive model that identifies the immediate and sufficient causes of failure. Now that you have the theoretical foundation and are familiar with the terminology, it is time to transition into the software itself. In Part 5, we will see the item toolkit fault tree module in action. We will begin the hands-on process of building the actual model for our reactor vessel case study, applying everything we've discussed so far. Thank you for watching, and I'll see you in Part 5.